Okay, so we are finishing up section 1.5. I know we just started it. What I would probably advise you to do is to write out everything first and then listen to the video. Because to save time, I've written out everything. I think mostly everything. So there are the homework problems again that will be due next Friday, and another partial derivative review. I want to do another one just because the other one I think was autonomous, or it might have been a special case. So I wanted to show you one where x's and y's were both involved, or maybe I did. I just wanted to show you one that was a little more elaborate than the last one. Okay, so I want you to write this down. I actually want you to see if you can find the partial derivative of the partial derivative of z with respect to x, and the partial derivative of z with respect to y of this above function. And again, remember that when you're taking whatever you're taking with respect to, you treat everything, all the other variables, as constants. All right, so pause and see if you guys can figure that out. Okay, so here are the answers. Okay, so that's self-explanatory. I'll leave that to you all. All right, I wanted to go back over example 3. Hopefully for those that didn't understand, to get a better understanding. But again, you need to, and I sent out the email about reading before class. Even if, I mean, you want to read for understanding, definitely, but just as long as you can see, and even if you only understand one thing or one topic out of each section, that's fine, because I guarantee if you're not understanding in class, I can guarantee that you're probably not reading ahead to understand it. Okay, so just keep that in mind, to sort of read ahead and make little notes of things you don't understand in your reading, and hopefully if I don't address it, then I will. Okay, so we had the dy over dx equals y over x, and we just wanted to talk about in terms of, because I think some of the homework questions just ask you to analyze, or what can you conclude from in regards to the existence and uniqueness theorem. So here we said that y over x is continuous. That's my abbreviation for continuous near the initial point x sub 0, y sub 0, as long as or whenever x sub 0 does not equal 0. So that means solutions exist as long as x sub 0 does not equal 0, and when x sub 0 equals 0, we know nothing. Okay, so we can't conclude anything. All right, and uniqueness is you have to do an additional step of evaluating the partial derivative with respect to y. And so we found that the partial derivative with respect to y was 1 over x, and this was also continuous near x sub 0, y sub 0, as long as x sub 0 did not equal 0. Okay, so we can conclude from that y of x sub 0 equals y sub 0, so our initial value problem is unique whenever x sub 0 does not equal 0. Okay, and because this is a separable function, we can integrate, and I want you to, so I started I did the separation, then I did the integral, and then we have here, and I actually want you to pause and finish in your notes. Your final solution should be y of x equals k times x, but I want you to check and finish that in your notes. Okay, so I want to leave that up to you. So in your notes, don't write. So if I ask to see your notes, I don't want to see finish in notes in your notes. I want you to actually finish them yourself, and then hopefully you'll get, you might use a different variable as your constant, but hopefully you get that solution. Okay, well, since y of x equals k times x, then for initial condition y of x naught equals y sub naught, then if we substitute it in, we can actually just solve for k in general, right? So k is y sub naught over x sub naught. Okay, and let's assume that we're given the initial value, the initial condition of y of 3 equals 2. Well, then y of x, then our solution when we solve for k is going to be y of x equals 2/3 x. Okay, you guys see that? All right, so y is 3 and x is 2, so 3/2. Okay, is our k. And notice that it contains the point 0, 0, right? It contains the point 0, 0. And y of 1 equals 0. well, I'm sorry, if we have y of 1 equals 0, then y of x equals 0. Okay, so it contains the point 0, 0, and so we have the solution. It's not unique, right? Because we have here y of x equals 0 and y of x equals 2/3 x, both going through the point 0, 0, so it's not unique at 0, 0. Okay, and we knew that already from the uniqueness that we showed. Okay. So to conclude that example, for initial conditions, 0, y sub 0 has no solution, but for initial value condition, x sub 0, 0, and I guess I should just call it initial condition. So for initial condition, x of 0, comma 0, that point, where x of 0 does not equal 0, then many solutions exist. So many solutions exist. And again, we're talking about, so don't confuse when we're talking about the initial condition, don't confuse that necessarily with looking at the point 0, 0, because as we saw, there are solutions that go through the point 0, 0, but the initial condition, x of 0 cannot be 0. Okay, so let's look at another example. So let dy over dx equals 1 plus y squared with the initial condition y of 0 equals 0. And again, you can stop the video and write this down and then come back to it. No, if we look at slope field, solutions blow up to infinity rather quickly. So if you guys were to plot this in Maple, you would see that the solutions blow up rather quickly. Autonomous, thus separable. And I want you guys to finish this, okay? So again, do not write finish in your notes. I actually want you to finish this, which shouldn't be too bad. All right, so you have the answer. So y of t equals tangent t is what you should have gotten. And if you recall, the domain for a tangent is from negative pi over 2 to pi over 2. And so we have our solution here with this shape, and if this model, so notice when t as t goes to pi over 2, it's blown up into infinity, right? And so I just want to make a note here. If this model is physical system, the system would break as t goes to pi over 2. We talked about a couple applications, and we really haven't we're going to get into more applications in the further chapters. Here we're still just learning different techniques with different equations and solving and analyzing the differential equations. But just know, so this would mean it breaks as t goes to pi over 2, it would break. Okay, so example 5, analyze dy over dt equal to 3y to the 2/3. So I want you to take a few minutes and just think about what do you know, or what can you say in regards to existence and uniqueness of this. So just pause the video and think about that before you go to the next slide. Okay, so here's our analysis. Well, f is continuous everywhere, right? So there's no bad values. The partial derivative, however, which you should have calculated hopefully, was 2y to the negative 1/3, and that's continuous everywhere except where y is equal to 0. Thus, we have no information regarding uniqueness for the initial value problem with initial condition y of t sub 0 equals 0. Okay, so that's what I'm looking for. So in the homework, that's sort of what I'm looking for. And in terms of, I think they ask questions about analyzing existence and uniqueness. So I'm looking for you to talk about the function itself. Is it continuous or not? And the partial derivative with respect to y. And then let's move further, and we're going to have a little more information. It's separable, okay? Also, we can also mention that it's separable. So integrate to find solution. Once you find y of t, consider the initial value problem y of 0 equals 0. Discuss the uniqueness for this IVP. Okay, so I want you to think about that and write that in your notes. All right, so write that down in your notes. I'm not going to talk about it, but write down in your notes. So once you find y of t, consider the initial value problem, y of 0 equals 0, and discuss the uniqueness. I'm sorry for that. Okay, so I think this might be in your book, but here we have this It's autonomous. It's an autonomous, but it looks, I don't even know where we would begin in terms of integrating that, right? And it has an initial condition. Okay, but because of this existence and uniqueness there, and you can actually, if you recall, the domain for sine and cosine are all reals, and then we have a polynomial. The domain for all polynomials are all real, and so there does exist solutions. And then we can also show, and you might want to practice, just for practice, find the partial derivative of these, and so that's gonna, finding the partial derivatives with respect to y, and that should also be continuous, and so it has uniqueness as well. And so if it's autonomous and it's separable, then you can integrate. Keep that in mind. I don't know if I said that explicitly, but autonomous means separable. Well, if it's autonomous, there are other forms that are separable, but if it's autonomous, then it's automatically separable, and then you can integrate it. Okay. And if y is, notice here though, even though we don't know necessarily how to integrate this or where to start with that, notice we do see some of our equilibrium solutions, right? So y equals 2, when y is equal to 2, the right hand side of that is equal to 0, thus y sub 1 of 2 t equals 2 is a solution, right? So we can call that's a solution to our system. Assume y, so let's assume that we had another solution, y sub 2 of t, that's what that is a solution with initial condition 0, y of 0 equals 1/2. By the uniqueness theorem, right? Because remember, that means with initial condition, so you're starting at that point and you're sketching the slopes along that curve. And so if we're starting from y of 0 equals 1/2, by the uniqueness theorem, this y sub 2, our second solution here, has to be less than 2, right? It can't cross 2. I was talking about that in class. With this initial condition. Also, y equals -2 is also a solution, right? Okay, so thus y sub 2 of t with y sub 0 equals 1/2 as the initial condition is bounded by the two other solutions we have on there, y sub 1 of t equals 2 and y sub 3 of t equals -2. So I hope that makes sense. Once you have, so knowing that a differential equation exists, a solution exists and is unique, can tell you a lot of information, even if you don't know how to find that solution explicitly. Okay. So I think the next couple examples I want you guys, so I'm really putting more autonomy on you all to really read the book and ahead of time and really try to understand it for yourself before I present it to you all. I think it'll just make your experience a lot better in the course, and we can maybe even do a lot more examples instead of doing more theoretical work or definitions, and definitions. So here I want you to look, so this is from your book about comparing solutions, and just see the book and summarize in your notes what they say about this example, and also see in your book on uniqueness and qualitative analysis. That was also in your book, and sort of summarize that in your notes as well. Okay. So I did want to, and I try to do this for each section because since you're doing the homework, I try to present a homework problem. So this is a homework problem 1.5, number 7. I'm pretty sure it's not one that I gave you to do. I don't think it is. But here we have this model and initial condition, and it's autonomous, of course. And so that means it's separable. If we wanted to, you would have to do a partial fraction decomposition on that, which may not be too bad if you wanted to find the actual solution. So you could find the actual solution here. And it might be a nice practice to find the actual, well, first, the question is, what does existence and uniqueness theorem, what does exist, I guess I'm missing a the there. What does the existence and uniqueness theorem say about the corresponding solution? So I think I have it on the next slide. I talk about it, but I want you to think about what that means. So think about existence and uniqueness, and with that initial condition, what can you conclude before you go to the next slide? And once we finish, so once I finish, which I'm almost finished, you might even for this want to try to find the actual solution y of t and see if what you thought is correct, or can you confirm anything further with actually knowing the solution. Okay, so Well, first we can say that f of ty, so that right side is continuous everywhere because it's a polynomial. The partial derivative is also continuous everywhere because that's going to be a polynomial. Equilibrium solutions are y equals 0, 1, and 3. And the sign chart for f, and this sign chart, let me say, because you guys will be doing a summary on section 1.6 and turning that in on Wednesday. This sign chart, if you think about when you read on equilibrium, so this is a little side note, when you read on equilibrium and phase line, really think about how does this sign chart come into play, because I think there's some similarities there with the sign chart and the phase line. Okay, so just keep that in mind. And of course, section 1.6, in case you haven't looked at it, is only dealing with autonomous equations, okay? So the sign chart for f is here, and since y of 0, so our initial condition equals 2, whenever, well, I'm sorry. I could have wrote that. I'm trying to look at my notes. I wrote this early and I'm trying to see if this is what I want to say. So since y of 0 equals 2, well, we know that that means y of 0 is between 1 and 3, okay? And whenever, yeah, I guess I can keep that. So whenever y of 0 is between 1 and 3, then y of t is going to be between 1 and 3. The solutions will also be negative, right? Because in the interval here, it's negative, okay? And this is just pictorially so you can see what's going on. There's our equilibrium solutions in red, our initial condition. So it's going to be bound, it's going to be negative. So you can probably get a sketch or probably sketch yourself how it would look and maybe confirm in Maple if you wanted to. But yes, so we are done with section 1.5. You should be A-okay, hopefully doing the homework, which is due next Friday. The take-home quiz, which I posted on section 1.4, is due on, I moved it to Saturday because they're doing some type of maintenance on Moodle, and so I moved it to Saturday, but you might want to just try to get it out the way earlier so you can be done with it. Okay, bye. I'll see you Wednesday.